You're welcome. Yes. Today we will be going to take a look at ownership concept. Ownership is the most unique feature of Rust. It's what enables security that Rust adds without using a garbage collection. So we will be taking a look at what is ownership. First, let me see if stream is fine. I think it is. Yeah. So, like, what ownership is, we will see about what ownership is later. But first, we have to understand like what is stack and what is heap. So every program needs to manage the memory somehow. Like it can be like languages like Python or Go uses garbage collection for it. Garbage collection means that it takes look at whatever memory used and it will free it afterwards. And some language use like we have to explicitly allocate and free the memory. Like in C, C++, we have if we allocate a memory, we have to free it, right? But Rust uses the third approach. It uses neither of this. It 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 manages the memory by system of ownership. Like and that rules are checked by compiler, so you don't have to worry about it. By worrying about it means like issues after compiling. They will get detected at compile time only. That's what I want to say. And as this is like new concept for many of us, they are explaining it here. And once we understand about it, we will be our understanding about the rest will be much better, and we will be using it much safely and efficiently. But first, let's take a look at what is stack and what is heap. So means if you have used any language like Python, you don't usually deal with stacks and heap, or you don't usually care about them. But if you have any system level language like C, Rust, then you have definitely worried about stack and heap, and they actually matter how our program is going to execute. They are both part of memories, but stack is like last in, first out. And so in short, I am not going to explain all these details. You can of course take a look at them and read them. But basically, so in the context which we need it, just a second. In our context here, all we have to consider is like whenever we use like declare normal variables or functions, they are getting stored on stack. Like our function has a stack frame and it gets executed from the stack. While if you want to like have some data which is of unknown size, it can grow or shrink later, then we use heap for it. Heap is not organized in any way. Stack is well organized, heap isn't organized. When we allocate on heap, what is that is our memory allocator goes find some chunk of memory of the space which is required, and it allocates it and then returns a pointer to it like, hey, I have allocated this much memory you told me, and here is pointer, here is address for it, you can access it now. And also we have to consider like in some languages, if we are allocating memory, we have to free it, else we will just run out of space. We have to return that memory to the memory manager. But in Rust, we don't have to do that much often, at least in basic uses, because of this. Because Rustful is it for us, and we will see about it how Rust does it later. Later means like no. But yeah. So first, let's just take a look at rules. Every value as a variable, and the variable is called as its owner, the owner of this value. Like for example here, this hello is a value and s is its owner, and every value can have only one owner at a time. There can't be like many owners, just one owner. And once owner get out of scope, the value will be dropped. That are just basic rules, we will see about them later. And as we know, we have already we are already enough familiar with Rust that we can skip this boilerplate, the main function and all that. So here our variable s is referring to a string literal, and this is its value. So if we take a look at scope, and we are using this block scope here, as we said in last videos also, like before declaration s is not valid because we don't know what s is, and when we declare this variable, it becomes valid until the scope ends. Like whenever there is closing bracket, this scope is now over and s will no longer be valid. We can't use s after that. S means this variable. So that's how the scope works. Like scope starts when we declare a variable and ends, like ends if whenever it is used last, or if we are using block scope, it will end with the block. So to better understand with the concept with heap, we will first have to take a look at a different data type which we didn't in chapter 3, which is called a string. And one thing to note here is that most of this type we take a look at in data types, they were getting allocated on stack, like integers. It's told here, later we will take a look at them also, but for now, what string is, it is basically it is basically this string which can be mutated, like changed or grown or shrink. When we declare it like string literal, we can't mutate it. This is immutable by default and we can't actually mutate it. But if you want to say you want to change this string, then we use, instead of, this is commonly referred as and str. And means ampersand for the reference, and this is we call a string. So here we are making variable as a we are calling from function from string here. So basically what we are doing is we are allocating the space on heap and storing hello there and storing its reference from yes. So what string is, here it is better illustrated in diagram. So yeah, this is how string consists of a pointer, a length and capacity, and pointer points to the value it's storing on heap. That's how the string is working, and we will see about them in much detail in chapter 8, like what are they in all that. So here is a quick example like how they can be mutated. We can declare them as mutable variable, and as they are on stack, we can just push string, and so it will push it on the stack after hello. So if we run it, yeah, it's saying hello world. So what happened here is first s was hello, but when we push the string on the stack, it got mutated to hello, and this got appended to it. So hello world. That's how it is mutated in memory. But what's the difference, and like why we can mutate string but can't mutate the string literals, or what are different types, means why are they different? So here in case of string literal, we know its size at compile time, also its contents, so we can store them on stack, but this property comes because they are immutable. So if you want to change grow the piece of text or shrink it, and if we don't know what's going to be its length and all that, we can use string type when we are using, and we are allocating it on heap, because as I said earlier, we use heap when we don't know the size at compile time. So there are two restraints to use heap. First, we must request memory to a memory allocator, like we need to allocate some memory on heap, and then we need to free it, right? We need to return that memory once our uses are done. So the first part of requesting memory is the done by this function string from. So this is how we are requesting memory to be to be allocated for this. And the second part is differently done by in different languages. Some languages use garbage collection, and like Python or Go, and the garbage collector takes care of these memories. So it clean up memory that isn't being used anymore, so we don't have to think about it, right? But if we are using some language that doesn't use garbage collector and we have to manually do it, and then it's a big problem, because it is known for causing many bugs or security issues, we can say, like memory corruption and all that. So we can't forget to free memory, or we can't free too early, or we can't free twice. Like there are a lot of issues. But Rust takes like completely different path. Like once we saw just like what is the scope of this variable, yes, right? So once it get out of scope, Rust will clear it for us. Here it is mentioned that the memory is automatically returned once the variable that owns it goes out of scope. So without using a garbage collector, it is freeing the memory for us, allocating for us and freeing also for us. So we don't need to worry about it. So what is happening here is when s goes out of scope, the this function is called as drop. So what drop will do is return the memory. And if you are familiar with C++ or used it for allocating and deallocating resources, it's called as resource acquisition in initialization. If you are familiar with this, and if not, you can just take a look at it if you want. And this pattern makes it very powerful, so that we don't have to worry much about freeing memory, or instead of worrying much, we don't have to worry at all. We just have to focus on this ownership now. So what happens if we do like this? Like while we are moving variables, if we say let x equal to 5 and let y equal to x, so you can pretty much tell what's happening here, right? We are copying the value of x to the y, so at the end both will be 5, like x will be 5 and y will be 5. But what happens if we do this with string, right? We made a new string which is hello, and the variable we are binding it to is s1. What will happen if we say let s2 equal to s1? So if we take a look at what s1 is, it actually consists of three things. First is the pointer and length and capacity, as I described earlier. So when we say s2 equal to s1, we are not saying that this value is equal to s2. We are saying this reference is s2. So it will look like this. Instead of making another value, we just copied this part. This is called as shallow copy, also shallow copy. And what is happening here is that both are pointing to same value, same address where the value is located. But can you see a problem here? If s1 goes out of scope, let's say this s1 gets out of scope, but s2 is still pointing to that address, so there is chance that we might double free the memory, and which is not good, which is another security issue, or we can say memory corruption issues. So how we were expecting it to be like this, like complete copy, so allocating this whole data at another location and then making s2 point to that another location. But if the data is more, like instead of just hello there is a lot of thing, then it will be like very resource heavy operation, so it will affect our runtime performance. So instead, how Rust deals with it is like this shallow copy. Once we copied s1 to s2, s1 becomes invalid, so we can no longer use s1. Here we can see the example in code. Here we had first s1, then we said s2 equal to s1, and then when we try to access s1 again, you can see here compiler is giving error, like we are moving this, we are value moved here and value borrowed here after move, like we have already moved the value, and once we move the value, the previous thing becomes invalid. Same, so we literally moved s1 to s2. Now we don't have anything in s1. That's what moving is. And also, and if we don't want to like just move it, we rather want to make it like this, so we can just use this clone method. See, if we run this code, what clone does is, instead of shallow copying, it completely copies the value from heap, allocate it in new location, and then returns a pointer to that new location. So you can see we just made a new value here. If you see the addresses of this, they are going to be different. They are going to point on different addresses. And as we discussed just now, this copying whole thing from one location to another location is pretty expensive. So calling clone function might become expensive, like comparatively expensive, not like it will be very slow, at least for small data. That's how it's working. But you know, we just first we start with this, and this compiled without any errors. So you might say like, why it's happening? So when we have like the types which we discussed in data types, such as here they are mentioned here, like integer types, boolean type, floating point types, character types, tuple, if they contain the same elements, they are basically allocated on stack, right? And copying from stack is very not so expensive compared to heap, and they can be copied so easily, so there is no point cloning them. We can just copy the value from here. It won't be very resource heavy or expensive task. And you can also annotate our types by copy and drop. But one key thing to note here is, if a type implements a copy trait, an older variable is still usable after assignment. Like this here, we are using copying it, but still X is accessible even after assignment. And we can't annotate a type with copy trait if any part of it implement drop trait. So these are just some things we have to, if we want to take a look at, we can always take a look at here for now. And these are types which implement the copy trait. Copy trait means we can just copy like this. Here we don't have to worry much about it. So these are just the basic data types. We can select whatever the basic data types are, we can just copy them. So here comes the ownership part of it. Is stream fine? Yeah. Here comes the main interesting part of it, like what is ownership. When we assign a variable or like pass a variable to a function, we are just giving our ownership. Yeah, passing a variable to a function will move or copy just as an assignment does. So as we did here, s2 equal to s1 here, same thing is here if we just pass it as an argument. So let's take a look at this code. What we are doing is this: we are declaring a variable called s, and which is a string, and then we are calling function take ownership. So when we call this function, what we are doing is we are passing the ownership of s with it to this function take ownership. So what happens here is string comes in scope, goes out of scope, and drop is called, because whatever the memory got allocated to some string has to be freed. And here also happens that x comes in scope, and then we call it make copy function. And because that x is just a 32-bit integer, we just copy it, like we don't have to implement the drop and all that, so we just copy it. There is not much things to worry about. And now here x goes out of scope, and then s, and because s value was moved, nothing happens here. If we didn't use this function, s value should have been dropped by here, but what we are doing is we are passing the ownership to this function, and this function is freeing that memory. So, and once we pass the ownership, we can't use s here. So let me just try to run it on Rust playground. Yeah, okay, if we run it, you should see the result here. Yeah, this take ownership function is printing the string hello, and this make copy function is printing 5. Now what happens if we, let me copy, if we try to print s here, let me run it. Yeah, you can see it didn't print. What we are doing here is like the same thing is happening here. What happened with this s1 equal to s2, then we can't access s1 anymore. So the same thing is happening with the functions. We are calling this function take ownership and passing s. So we are basically passing s ownership to this function, which goes here, and once the scope ends, Rust knows it has to free the variable, so it frees the memory. Sorry, not variable, the memory. And now we have already passed the s, so s become invalid because we passed its ownership to here, some string. So s became invalid, and we can't print invalid things, right? Here it is explaining the same thing. This value is moved here when we call the function. So calling a function is same as assigning like a variable we saw. So what is like, we can also do this when we as we transfer ownership while calling a function. Same goes with returning. When we return this, like see, give ownership function, we are declaring a string, and when we return this string, this is an expression, so we are returning it to the s1. We are actually transferring the ownership to it, right? So passing the argument or returning something from the function, we are transferring the ownership of it. So here, if we run it now, it should work just fine. These are just warnings, and we are not printing anything, so this is like we are not using this, so they are saying unused, just prefix with an underscore, and we are not printing anything here. So what give ownership does is that inside this function it declares a string and gives its ownership to s1. s2 is just basic declaration here in this scope, and what s3 does is it gives the ownership of s2 to this function here, and then this function returns the ownership again back to s3 here. So in short, if we try to access some string here, we can't, because we are giving its ownership after this. Once we are returning it, we are just giving its ownership. But one way to get around this is like this. We have a main function, we declared a string, and when we pass it to function, we are giving its ownership, and once the function is done, we are returning two things. We want to calculate length, right? So we are returning length as well as the string. So we are returning the ownership also. So it becomes, and we are destructuring the tuple as we did last time. So s2 becomes valid and the length gets assigned to len length. So, and this doesn't look quite nice, right? We don't have to do this all the time, and that's where the references comes in place, which we will see about tomorrow. So we don't have to do this ever again like this. This doesn't look right? And I highly suggest you to take a look at this what is ownership chapter on your own also, so you will get some better understanding. I will put link in chat if you want. Yeah, if you have something, let me know in chat, or I will just end the stream. Okay, then see you tomorrow. Bye.